Since we will look into whether two or more concurrent threads are correctly handling shared variables, let's introduce a system model for the critical section problem. From now on, we assume each of our threads looks like this. We have a loop that runs forever. It's a model, of course it will stop in practice, but from the model perspective, we do not assume anything about when it will stop. Inside the loop, we have a critical section, the one in which we read or write shared variables. We assume shared variables are accessed with atomic read-write operations, so only one read or write operation can be performed at a time. Before the critical section, we have an entry section, a statement, line, multiple lines, whose execution implies the critical section can start. You can see the entry section as the portion in which the thread is trying to acquire a lock, its right to enter its critical section. After the critical section, we have an exit section, a statement, line, multiple lines, whose execution implies the critical section is over. You can see the exit section as the portion in which the thread releases its lock for someone else to enter their critical section. And a reminder section, basically the rest of the code in which we do not worry about reading, writing shared variables. Notice that for simplicity, we also assume thread's execution does not fail. Our goal of having two or more concurrent threads correctly handling shared variables can then be formulated as define an entry and an exit section that ensure mutual exclusion, progress, no deadlock, no live lock, and fairness, bounded waiting or no starvation. Mutual exclusion means that only one thread at a time can execute its critical section. Progress means that if no thread is in its critical section and one is somewhere trying to enter there, then one must enter its critical section in bounded time. Notice that we do not make any assumption about the duration of the reminder section of a thread. A thread can stay there for as long as it needs. The duration of the reminder section is not bounded on time. Let's put also a temporary extra assumption for now that we only have two concurrent threads. If you want to visualize such behavior, it looks like this figure. As you can see, only one thread at a time can enter the critical region. If thread B tries to enter it when another thread A is in it, then B waits. What we are going to do next is to look at various ways of defining the entry and exit section and ask ourselves, does solution X ensure mutual exclusion, progress, and fairness? We want formal correctness proofs. We cannot answer with it looks like it does, nor with I tried running the code 1 million times and it never broke, so I'm confident it does. To provide a formal answer, we are going to try to find one execution of the threads that breaks one of the properties. If we find it, then the solution is not valid. It breaks one of the desired properties. If we show such an execution does not exist, then the solution is valid. Let's try to look at a specific simple example, which we refer to as check completion. Let's say the code of our two threads, A and B, looks like this. They both share two Boolean variables, flag A and flag B, initially set to false, which they use to indicate their intention to enter the critical section. Here I show A's code. B's code is symmetric. In its entry section, A waits as long as B's flag is true in a while loop. This is called busy wait because A is using CPU cycles to spin in a loop. The loop ends when B sets its flag to false. After that, A sets its flag to true, enters the critical section, and when the critical section is over, sets its flag to false. Is this solution to the critical section problem valid or not? I strongly suggest you stop the video and try to reason and provide a formal answer. Now, let's try to answer the question together. That is, let's try to find an example showing one of the properties can be violated. Can the property of mutual exclusion be violated? For instance, can A enter its critical section while B is in its critical section? Let's answer the question with the help of this drawing. In this drawing, we see that A enters its critical section after B entered its own, but before B exited. Can this happen? To happen, sometime before entering its critical section, A needs to set its flag to true. That's what the code says. And before that, A needs to see that the value of flag B is false to exit the busy wait while loop. Again, that's what the code says. Now let's focus on B. To enter its critical section, B needs to set flag B to true. That's what the code says. Now we are at a critical point. In our example, if we assume B sets its flag to true before A sees flag B value is false, then it means in between these two events, B completes its critical section. Otherwise, A cannot see flag B being false. In the example we are studying, the point in which B sets flag B to true comes after A sees flag B value to be false. So now we are left with one question. Can B see flag A being false in between the time A sees flag B to be false and B sets flag B to true? The answer is yes, because flag A is initially set to false and is also set to false every time A exits its critical section. So in the figure, the portion of time during which A has not yet entered its critical section is a period during which flag's A value is false. We have found an example that breaks the mutual exclusion, which implies the code is not a solution to the critical section problem. Once you listen to this argumentation, you digest it and you understand it, you will probably agree that proving whether a solution to the critical problem is valid or not is very challenging. In the following videos, I strongly suggest you stop and try to formally find out yourself whether a solution is correct or not.